All right, this is slide 30-42, and it's looking at a bit of revision for how we did this experimentally, working out the amount of energy. So we did this at the beginning of the year for fuels, and we used the specific heat capacity of water to find the amount of energy released from, we can use it now to work out the amount of energy released from food. We did it to look at fuel before. We just needed to measure the temperature rise of the water and the mass of water. So we're using the specific heat capacity of water. This experimental way of doing it is really bad, and the next method is going to look at the fact that most of the energy is lost from the container, so you're not really getting a very accurate amount of energy. You're not trapping all of the energy. So we're using this equation. Q equals mc delta T is kind of an easy way of remembering it because it rolls off the tongue, but you can build up this equation. If you know the specific heat capacity units, they'll cancel. So this is in your data booklet. It's in joules per Kelvin per degree, which is the same thing. Every Kelvin is the same temperature rise as a degree, the same increment. So instead of doing it at the beginning of the year, we did it with our spirit burner, and we had our fuel that we were looking at, and then we had the big bulb to trap the heat in water. But same idea, that we're using the specific heat capacity. So specific heat capacity is the amount of energy, joules, for every gram of that substance to go up by 1 degree. And you can see by looking at the table that water has a higher specific heat capacity than lots of other things, and that's why we're using the water to trap the heat to measure the amount of energy. So basically all we need to do is measure the change in temperature, how many degrees has it gone up, and we need to know the mass of water, because each of these things will need more energy to increase the temperature and more energy depending on how much water you've got. So first question, a sample of burning food is used to heat 100 mils of water. Calculate the heat energy in kilojoules that has been transferred if the temperature of the water increases from 18.5 to 44. So we're just measuring the amount of energy that's been put in there if the temperature goes up by that amount. So Q is energy, and your specific heat capacity is 4.18 joules for every gram for every degree, and we know that we have 100 mils of water, so we can assume that the density of water is taken as 1 gram of water for every 1 mil of water. So 100 mils of water has a mass of 100 grams. So we can just substitute, because if we assume the density of water is 1 gram per mil. So we know the mass of the water, and we've got the temperature, change in temperature, so the amount that the temperature has increased by. So if we take that away, we can work out that it's gone up by 25.5 degrees. Some questions just say that it increases by that amount. Some questions will give you the initial temperature and the final temperature, and you have to work it out. So you can see that these units are going to cancel, grams and degrees, and then you'll be just left with the amount of energy that caused that temperature rise. Often you need to turn this into kilojoules, so just check, have you finished answering your question? Calculate the heat energy in kilojoules. So you do need to, in order to get the extra mark, or to get the mark, that you need to answer the question totally. We have 3 significant figures here and 3 significant figures here, so your answer needs to be in 3 significant figures. Can you make sure, when you're converting from joules to kilojoules, this is a larger unit, that the number goes down, and that you have actually divided by 1,000 correctly, and move your decimal place correctly, and round it up. So this number, 50, anything from 5 and above, we'll round up to 7. So if that was 49, it would round down to 6. Be careful that you're rounding correctly and converting correctly. So this question, same idea, calculate the energy, but this time we want to know the energy for each gram of food. Okay, so we've got two parts to this question. So the first part is what we just did in the previous question. We have that much water, so that many grams of water, and our temperature has gone up by that amount. So you don't need to work out your initial and final. It's told you that it's increased, so it's told you the change already. So you want your energy in kilojoules, so you need to change your joules to kilojoules. So that's how much energy we have trapped in here, and we are assuming that that is the amount of energy that's been released. You can see that clearly we're going to lose a lot of energy, so this amount of energy is always too low in this setup. We can work out this is the amount of kilojoules released for that many gram, that much of a biscuit. If we wanted to know how much, hang on, I've jumped straight to, this is our initial amount and it's given you a final amount. So the difference in that is the amount that you actually turned into carbon dioxide when you burnt it. So you do need to be careful and don't do what I just did then. Just assume that that is your total mass of biscuit. You need to make sure that you know if you've got an initial and final that you look at the amount of biscuit that was burned. So you've got how many kilojoules for this amount of biscuit that was combusted, how many kilojoules if you had 1 gram. So if you divide any number by this, you'll get the amount of kilojoules for 1 gram. It's basically just your ratio. When you take this over the other side and multiply it by 1, they'll cancel and you'll just be left with the amount of kilojoules for 1 gram. Okay. So we've got this amount of corn chip was burnt under, so we've got after the flame went out, the mass of the corn chip was this. So we've got our final and our initial, so we still need to work out the difference, the amount of corn chip that was turned into carbon dioxide. And you've got this mass of water and the temperature rise. So same kind of question as the previous one. Work out the amount of energy that's trapped in the water in kilojoules, and then work out you've got that much kilojoules for that much biscuit that was combusted, and then you can work out how many kilojoules for 1 gram by dividing this and this. Ethanol is a common fuel, so we started off the year looking at, instead of food, we started looking with fuels, so this is like our initial Unit 3 kind of questions. Burnt in some, so this is trying to take account of the amount of energy that's been trapped by other things other than the water. So if we looked at the cooking pot and its temperature, its specific heat capacity, and the temperature rise of the cooking pot, so calculate the minimum amount of energy required to heat that much water and the pot from this temperature to this temperature. So you need to look at the specific heat capacity of both, work out the amount of energy to increase each of them, that amount, and add them together. So if we just look at the water, we know the specific heat capacity of water and the temperature rise, so we can see that you need that much energy for the water, and the temperature rise is the same. we need the mass of the pot and the specific heat capacity of the pot. And then you've got those two energies, the amount of energy that's heating the water, the amount of energy that's heating the pot, and you can work out the total amount of energy. So this would be one way of calculating the amount of energy that was lost. It's not calculating the amount of energy that's lost to the air though. Okay, this is another ratio question. So just a bit of practice. We did that this amount of energy is for 1 mole of ethanol. So we know that you need 1364 kilojoules for every 1 mole of ethanol. So what mass of ethanol needed to be burned in order to make this much energy? So we know we can work out the amount of moles and then just turn that moles into mass. So the amount of energy that we had was 198 kilojoules. How much ethanol would you have needed to make 198? So how many moles? So using our ratio, how many moles if we know that we trapped 198 kilojoules, and we know that, so we can make our ratios. When we know that this is kilojoules for 1 mole, you can flip that over and have how many moles for that many kilojoules. So you can set ratios up when you know those two numbers go together. You can put them whichever way around that you would like, so that you can get them in the right positions for here. So these two have to be the same and these two have to be the same, so that when we take this over the other side, the kilojoules will cancel and we'll be left with the number of moles. Once you've got the number of moles, then you can just convert that into the mass. So that's how many grams of ethanol you would have to burn to get 198 kilojoules if all of it was trapped in the water and the pot. And that's what I was saying before. Just remember that this is in your data booklet. Presumably you guys remember that by now, but it's mentioned as Kelvin. A Kelvin has the same change as a degree, so you can just substitute kelvins for degrees for this.